Good afternoon, ladies and gentlemen. I'll start with my short explanation with that mini conference about DEMAT project. This is DEMAT. The title of the project is Dematerialized Manufacturing System, a new way to design, build, use, and sell European machine tools. Let's see the outline for the presentation. We'll make a short overview about DEMAT project, partners, the consortium, the views and the like, the vision of the project, the target, the expected impact of this project in terms of energy consumption of material resources, and the like. These are the main figures of the DEMAT project. This is an European project funded within the 7th framework program, within the NNP priority. We are 16 partners from 8 different European countries, and the budget of the project is of 4.7 billion euros of budget, of which we have a funding of 3.5 billion euros all working during 42 months from the beginning of July 1st, 2010 till the end of next year. Let's discuss a bit about the vision of the project. The project we have seen in the title that we want to dematerialize the machine. When we think about dematerialize, the concept of the project is to remove material from machines. To remove material for sure while maintaining the functionalities of the machine. So, just as a starting point, if we see, for example, the machines along this curve, we see that on the one hand, mass consuming, they consume a heavy and big size structural components. So we can distinguish between low mass amount machines and high mass amount machines. So thinking about this difference, the structure of the machine has two main functionalities: to hold the components and peripherals, and to withstand process forces in a robust manner. So, thinking further about this issue, we see that, roughly speaking, only 25% of the mass of the machine is devoted to holding components and peripherals, where the remaining 75% is devoted to making the machining process to take place in a robust manner. So here we go to the core of the DEMAT project. We want to assure the functionalities exactly this high amount of the machine that is devoted just to make the machining process take place in a robust manner. So this is the approach of the project: to reduce the mass of machines while maintaining the added value measured in terms of productivity, accuracy, and reliability. Approach. On the one hand, the first approach is to reduce the mass of machines while maintaining functionalities, and the second, complementary and additional approach, is to increase the immaterial added value of machine tools. So, the view of the project is that we combine the maximum of added value linked to machines, while at the same time we use as low as possible material resources. So this is the model of the DEMAT project: maximum of added value with minimum of material resources. So we will start with the first approach: how to design a machine tool assuring the functionalities. So if we think about a machine tool, three main lines, three main areas can be solved: the mechanical point of view, the control of the machine, and the process itself, the machining process. So the approach of the MAT project is on the one hand to tackle a combined mechanics and process approach so as to assure that the machining process takes place in a stable manner, combining the dynamics of the machine with the dynamics of the machining process. The second approach is to combine the mechanics view with the control view. Once we have optimized the structure of the machine, we want to think about the control of the machine motion using a minimum amount of inertia in the heat drive of the machine. So the first approach assures productivity with minimum structural mass. The second approach assures accuracy with minimum mass, minimum moving mass. And the third and complementary approach is to combine the process and control view to control the machining process. So this assures reliability of machining process with a total minimal amount of machine. This is the approach, the technical approach of DEMAT. Think about machines that can be productive, accurate, and reliable with minimum of mass. So the first approach tackles about designing machines in which we optimize the design process using the following variables: the orientation of the machining mode, the stiffness of each mode, and the damping of each mode. We can combine these variables always with the view using the minimum possible of material amount. We also think about making the machine severe and productive processes that, for example, for the DEMAT case study, we have considered this specific case, this wrapping process with a minimum of mass in the machine. This is a real case study in which we have started from a supra machine of Nicolas Correa, and we have removed, for example, 60% of mass, of weight in the RAM, and around 41% of mass in the column. We are talking about a machine in which we are optimizing the mechanical behavior using lightweight materials like composite fibers, blocks made of those materials, aluminium, and the like. And at the same time, we made some simulations that assure that while we are removing mass to the machine, we are capable of assuring the stability of machining processes. For example, simulation of that machine in which we have removed 50% of the mass, and we have two structural modes that are limiting the stability of the process. So this is a diagram, a polar diagram that shows that with this ultra lightweight machine, we are capable of assuring this measurement is how depth we can machine with that lightweight machine. And our minimum objective is 1 millimeter. So we have removed, in some cases, even more than 50% of the mass of the machine, and we have almost assured that we are capable of machining at least 1 millimeter depth. Anyway, we can further improve that behavior without adding more mass to the machine by using active element chart that shows and the introduction of inertial damper in the machine, with which we assure the same productivity of the original machine that had 2.5 times more mass this is the original machine. This is the productivity of the original machine. Now we remove around 60% of the mass of the machine, and we are capable of assuring that the machine is capable of machining with the same performance. This is the core of the DEMAT project. So the key point here is that with this approach, we are capable of decoupling the material structure of the machine of the production result. We can maintain and even improve the productivity of machines while removing material, while removing mass of machines. This design approach of the project, this integrated mechanics control process approach, is complemented with additional research projects, sub-projects that aim at improving the added value of those machines. For example, one of the approaches is to think about new business models that can be linked to this lightweight, to this modular machine. For example, these are two innovative business models that are being developed in the DEMAT project. One of them has been called the paper-optimized product service, that is to assure that by means of modular blocks, we are capable of reconfiguring the machines to the variable demands of the market. And the second business model is the so-called paper-optimized capacity view, in which the user pays for having ensured that according to the variable demands of the market, the service provider will be able to provide machines that are reconfigurable and even to adapted to those variable demands. So these are new ways of making business linked to this new generation of lightweight and modular machines. Also, another way of complementing these machines is to have a sort of database in which we are what we have called the DEMAT information sharing platform, in which we have life cycle information about this machine. And for example, that information can support the negotiation process. We can store information such as the mass reduction linked to this machine, the energy reduction, the cost associated to this machine and the like, and also that information, the monitoring of the time between failures, the monitoring of the energy consumption, and the like. These are different approaches for improving the added value that is linked to a machine. And finally, just to finish, just a short view, short thinking about the impact that is associated to removing mass in a machine. This is an actual life cycle assessment that has been conducted on an actual machine, in which we can see that around 59% of the total life cycle impact is linked to approximately half of that energy consumption is linked to machine motion. So, approximately around 45% of the machine impact during the whole life cycle is linked to the material content. So, if we remove half of the material content of the machine, we divide into two the environmental impact of that machine. This is also the cost, the life cycle cost of the machine, in which we see that approximately 40% of the life cycle cost of the machine is linked to the material content. Is linked to the cost of the material, is linked to the maintenance that is directly proportional to the amount, to the size of the component. So this allows telling us that removing 40% of material in a machine while maintaining their functionalities allows reducing in the same percentage amount both the total life cycle impact and both the life cycle cost that is linked to the machine. So these are the main features of this DEMAT project. So for the case that there is any question, I will be very pleased to discuss about it.
So the machine
we have made some laboratory experiments in a Correa machine. We haven't. Our idea is to build with around 30% of the mass of a conventional machine, and to make that machine remove material. That is our objective. We have made some pre-laboratory experiments at Nicolas Correa workshop, in which an increasement in the productivity, for example, by using active dampers. So now we are doing the opposite. If we are capable of increasing the productivity without increasing the material of the machine, now we will do.
After that is simulation about the price of the machine, how the machine with the new solution is cheaper or more expensive than the regular machine.
Right now, if we use, for example, a sort of blocks made of composite materials, the cost is just comparing conventional structures with this sort of lightweight structures. The cost is 10%, 15% higher. But we must think that we are thinking about ad hoc structures in which we buy and we assemble structures just for this demonstration. 10%, 15% higher. Just thinking about one machine is not remarkable. We are not talking about higher cost, while we are thinking about a machine that will weigh